Hi, welcome back to Foundations Enterprise DevOps Source Code Operations. My name is Dennis. Let's go ahead and get started. Our learning objectives today include making decisions on selecting different programming languages for the sake of modularity, also known as decoupling. We want to convert functional code from other languages to Python and also be able to package your code into containers. Let's go ahead and get started. So, modularity selection. It's important to understand that not all programming languages are best fit for all solutions. Python may not be the best choice for every single solution, so you may have a multi-stack solution such as C++, C Sharp, Node.js, Golang, and many others that could be a part of your solution base. It's up to you to select which ones you need, but also understand that based on your comfortability and your capabilities with different programming languages, it might be easier and faster just to get as much done using one programming language and then decoupling it with hybrid services as opposed to utilizing purpose-built specific languages. We'll go over some of that in the modularities. First and foremost is going back to and revisiting our programming fundamentals, compiled versus interpreted. Compiled languages include the C family, Pascal, Fortran, Go. We have interpreted including Python, Ruby, JavaScript, PHP, and really Java. And remember that compiled languages, assuming that you have very efficient code, run just as fast, if not faster, than interpreted languages in most cases. Interpreted languages are better for portability purposes, so across operating systems, as long as you have the just-in-time virtual machine to actually interpret the code into machine code for you. Now, there's packers, or they can provide binaries and turn interpreted languages into a binary. So basically, it's just a binary launcher that you have a single package in there, and then you can actually unpack it, and there's a built-in portable interpreter without installation. Choose your languages carefully based on your use cases. Remember that C and C++ tend to work really well with hardware, mathematical calculations, and Python tends to work well as a great backend for web services. Here's one that we haven't shown so far in our labs and different interpretations. We have Golang example here, and pause the video and try to figure out what is going on and how you would actually do the same thing inside Python. I'll wait. All right. So hopefully you got the idea that let's take a look at what we're doing here. And let's go ahead and make sure I can click my mouse. There we go. Now what we have here is our package that we're saying. We have some keywords here. We have, even if we've never seen the language before, we have net and HTTP. Okay, so it might be doing something across the network. Our output is hello world to some sort of website. It builds, and then we have a starting our main application. We want to print something based on an HTTP request. And then we could print something else based on a different type of HTTP request, depending on our header information. Finally, we call that information to our main, and we're listening on a port 8090. Does this sound familiar? If it does, you should remember that we have Python Flask as the equivalent. The Flask server will actually do the same thing. You define your function right here based on your application route, and then you run that based on the listener. Here I use port 8000, but you can use 8090. Notice that we have pretty much the same requirements, and that's how you would port it over and translate. Remember to read the documentation and understand your syntax. Don't be afraid to flip between both slides here, so you can have a really deep understanding of what it looks like from one language to the other. Now, microservices, containers. Now, everyone's talking about Docker. Some people talk about Kubernetes. Really, these are all technologies that complement each other. Microservices have been around for a long time. In fact, really didn't become too popularized until Docker really came out, until about the mid-2000s or so. The idea is that the containers, at least with a Docker-based solution, includes the build, pull, and run. You have a Docker host running the daemon just like you would with a interpretive language, and then you have images that you turn into containers. Now that might be a little confusing. Remember, a container is just a running version of an image. So in this case, we have a registry which has the equivalent of our code repo. The reason why we call it registry over repo is because registry means that you're registering an application. So something's already complete for you. You're not actually repositorying code, even though it is compiled of code. A registry is based on images. The images, such as an Ubuntu in our case, or image can be pulled down using a Docker pull command. You can Docker run the image, and it becomes a container because a container is a running version of the image. You can also build images based on each other, and we have these called in layers, and we'll see this in the next slide. First, let's look about containers versus serverless. Now, let's go back here. Containers are really all about a runtime environment. So you can have your code running in a runtime environment, such as Ubuntu, Python, depending on your image and your build spec needs. A microservice serverless solution has all this going for you, so you only have to worry about interfacing with it, usually through a REST API. Now, REST APIs use the HTTPS protocol, like methods like get, post, head, and they do it against a listing, a structured listing, such as the root listing or headers that you saw earlier. Right? Those are potential APIs. And then the ingestion could be many different things. But however, in the Amazon Web Services world, many of the APIs ingested require JSON and as well as output JSON. So we have different services here like Amplify, Cognito, API Gateway, and ultimately serverless is serverless from your perspective. Pause the video, flip between the container and the serverless slides to understand more. All right, going back between container. So let's go between container, right? We have something that's a built-in image runtime. We have to still put our code in there. A serverless service or an API is already built for us. We don't have to manage a container or infrastructure. Hence, the server part is hosted, in this case, at Amazon Web Services or AWS. And you simply utilize or consume the API and let them process it for you and let them scale up and scale down for you. With containers, you actually have to utilize different infrastructure. You might have to have multiple containers as part of a single API. And they have to be behind a load balancer. So there's still infrastructure involved, whereas serverless has no infrastructure involved, at least infrastructure from your perspective. All right, no course is complete related to development without using containers. We're going to have to use containers at some point. Now, ultimately, the goal is to at some point move to serverless solutions, making it easier for us as developers or DevOps to focus on the code and only the code. However, because it took so long to get demodulated from servers, such as the three-tier architecture, so still servers, ultimately going to virtual machines, so three-tier architecture inside the single hypervisor server. We're now at containers, where you can have containers with multiple tiers of architecture and scale up and scale down based on runtimes and across different OSs and platforms. And while this may not be your most keen solution versus serverless, it is also a solution that allows you still customization, flexibility, and if you don't like AWS for whatever reason, if you build your solution as a container, you can actually port that container or container image in this case to another solution that supports containers, such as Microsoft Azure. Now, speaking of containers, when I'm scaling up and down and we need infrastructure, you utilize something called an orchestration layer. An orchestration example includes Docker Swarm or Kubernetes being among the top choices. Control and clusters include a management plane, which you have a master, which is kube control based on a kube server. And you have nodes based on a series of clustering. You can have the API runtime, so you can have two containers, so container 1, container 2, and they can be the same exact API running your container. You put them behind a load balancer and you scale up, you can have a highly available API or container application service. Now, containers are more just APIs. You can make them a whole application. They don't need to go across the network. Let's say you have a isolated use case where you just have to have the program running and keeping the data on the container or pushing it to the host. It really doesn't matter, but in many cases, containers can be across networks, and that's the whole point of it. Now, when you have no connectivity whatsoever, there's limited use cases for them, as I've mentioned earlier. So the point is, most of the containers actually have some sort of network connectivity. Hence why you still have infrastructure such as a load balancer. The whole point is to have orchestration. When a node goes down, a container or new container image should be spun up over here into a new node, such as an EC2 instance. To maintain your scalability and requirements, it really depends on what you're looking for. Kubernetes is one such container, actually funded by Google. A lot of development was made by Google and became quite popular. With Amazon, we have AWS EKS, which is the Elastic Kubernetes Service. So you actually have the flexibility of having open source software and standardized functions that you can port elsewhere, but bring it into a managed service. So you don't manage these servers anymore. You're only managing the fact that you utilize them and configure them. Inside the Docker ecosystem, I mentioned images versus containers. Remember, an image is something that you go from a registry, you pull it down to a local cache, and then you run it, which makes it a container. Your client could be the Docker client, or it could be an API. Look at the flows right here. Pause the video and let's look again about what the flows look like and what they mean to you. Okay, hopefully you had some time. Remember, green right here means you're running a container from an image. Orange means you're pulling it down. Basically, you're doing the same thing as a git clone. And then your build is saying, I'm going to build based on a specific image or a from scratch image, which you need the SDK, the build SDK for. So read up on that documentation if you want to build a complete container from scratch. However, remember, development and DevOps is not all about reinventing the wheel over and over again. Utilize some of the best practices based on official containers such as Python, Ubuntu that have come from the sources direct versus redoing it from scratch yourself unless you have a very, very specific use case. Now, container concepts. We have a base image now that you understand the process. The base image could be Debian or Ubuntu or the Python runtime itself. The boot file system and the kernel work together as part of this base image. And then anything that you do from a Delta standpoint, you can add changes to that, and your new image becomes a container. We define this using something called a configuration file called a Docker file. This is similar to something that you might see in CI/CD pipelines, such as a Jenkins file. But remember that your container is the writable portion of an image runtime. A writable portion of your image runtime. Now think about that. That means if you run an image, let's say our ultimate image right here, has Apache Emacs, your application writes to text files on the temporary portion of the container, well, that's the writing to the container portion. The image itself is a read-only based on your Delta. If you build a new image, right, each new image is a revision build against the old layer of the image. We'll see this in the lab, but I want you to get a good understanding of what this means ahead of time. How do you build an image? Again, I mentioned Docker. Docker file is essentially the configuration file. You'll make this in your lab, and we'll specify what we're looking to do. You build an image, and then your image gets run and becomes a container. You stop, start, or restart a container based on your image. You can also back up or save your images, and then push it to a repository or pull it from a repository. Again, just as a reminder of how this process flow works. All right, let's take a quick break, and then we'll understand some of the build spec file requirements of your Docker file. And welcome back. I hope you had a great break. Let's go ahead and get started on learning what Docker file looks like and how to actually build your own image. Now, there's a lot here. Take some time, pause the video, and understand what each one does. We're not going to use all of them in our lab. However, you should be aware of all of these to understand and get the most out of building your own image so you can actually run containers in the way you're looking for. I'm going to highlight just a couple of key points here. Let's go ahead and grab our item right here. The add command allows you to add files from the host system to the container, like dragging and dropping to a specific folder from your host to your virtual machine. That's the equivalent. The command, just like what you see here, allows you to run the container, a command when the container starts, right? So at startup boot point. Entry point allows you to run a very specific container executable, and then you provide parameters based on the command parameters. So these two kind of work together. Now, You can also have additional ones such as environment variables, from, maintainer, which is like comments in here. So you could have the maintainer of the build being your name and email address in a string. You can have hooks that trigger additional container builds or settings. You can set the default user content. So if your container, for whatever reason, needs to run as root without sudo, unfortunately, then maybe you could do that. And of course, you also have a working directory, which says, hey, what is my print working directory? And remember, the default working directory in Windows cannot be the directory, must be empty. It must not be in C in Windows. And of course, finally, we have run. Run allows you to execute a command and save the result as a new layer image, such as running a command for apt-get and installing Apache. And then it becomes a new layer of your image and a read-only portion. So your delta there. So how do we containerize something? Well, let's take our API example. Right here, we use Flash to our left, and we're going to listen on port 8000. Now, however, this is not going to necessarily work for us. And keep that in mind as we go through. Let's run it locally first. Well, we'll do our best practices, which is utilize a virtual environment. So combine all your pip installs into the same folder after you've activated your environment. In PowerShell, use a dot and then use the activation script accordingly. You know you're inside your activated virtual environment runtime when you have the green interchange of your actual prompt. In Linux and Mac, you'll use the command source, and it'll change your prompt for you as well. I'll install our dependency like Flask. And then, what else do we do from here? Well, that's our first step of preparation. Let's continue forward. Next, we'll freeze our requirements. Now, we haven't used pip freeze before, and the reason why we use virtualization, or VM, is because now we freeze the actual installed dependencies, not from the host, which could be a lot. We freeze it from your virtual environment activation. So now we create a file called requirements.txt. And so as you're creating and containerizing and packaging your solution to run in a container, you'll have requirements.txt for your actual pip install to say, I need to install all of these for my application to work. And next is the Docker file itself. You want to create a new Docker file, and remember that everything is case sensitive. So I like to use lowercase whenever possible. I have my Flask application in app.py, and I have my Docker file without an extension. You can use comments with a hashtag right there, or a pound sign, and you can say from a different image, and in this case, I'm using Python 396 Bullseye. Now, go to Docker Hub, which is hub.docker.com, and then you can actually look for registry image names based on what you're looking for, such as Ubuntu. I'll set my working directory to be /user source app, and then here's the interesting part. Let me actually, here's copy command. So instead of just adding a file one by one, you can do a copy. I can copy not from my container to my host, but I can also copy my host to the container. So copy from the current present runtime environment, which is, this is my path right here. Copy all of these files into the working directory, right? Into the working directory, which is /user/source/app, to go ahead and make sure that those copies are there. That's a simple application. Other applications may not have it so easy, but it's your job to make it easier for yourself. Next, I'm going to run, right? It's creating me a new layer, right? And creating that Flask application layer by installing the requirements into my new runtime. And next, I go ahead and utilize the command function to say Python 3, and then of course, all of my parameters right here. Now note something here. I have a tac port, and that was specified inside my original code, which I have to take out any.run for. Going back, if you comment this guy out, you would utilize this on an external container because you're running it from the outside, not from the inside at this point. I also comment out command and entry point. So if you didn't have additional parameter information, or if you want to use entry point, which is utilize Python 3 specifically, I can actually say Python 3 and then my single command right here, which is formed in the value of a multi-case list. It's an extra prompt I don't need, and for those of you who are programming with different languages or perhaps using different use cases, entry point might make a little bit more sense depending on your use case requirements. Now for our image build. Notice that I have all my files right here, and because I've already had my Docker file described right here, I use the build command, and I use attack T for my Docker API, and then I say use the present folder with the additional dot, right? So if you're looking for what the attack T makes sense for you, remember the man pages inside Linux, or look at the official documentation from docker.com. Now I can use Docker images to check my Docker API, which was what I named it here, to the latest image ID. And notice that the size is almost a gig, which is 940 megabytes. However, when you think about it, and you're going, why do all this for a simple Python script? Well, you still, in a traditional VM, would still have a multi-gigabyte Ubuntu OS. You'd have to install the Python runtime and then run your script, which could be much larger than 940 megabytes. This has been optimized specifically for your use case and needs. Then when a Docker run and then publish. Now the publish, tech publish, means turn on the local NAT-based networking, virtual networking from your daemon host to your container. This is the outside, which is your used for accessing your Docker container from your local host. So 8,000 in my case, I keep it the same for consistency. Or you can have your local Docker container running. Remember that this right-hand side is actually what you specify right here. Your left-hand side, right? Let me just clear this out. Your left-hand side is what you put in the browser right here. Okay? That's all that really means. And now we have hello world and our container running. To stop your container, make sure you do a container ls and get the information name. You want to stop it based on the container ID, not the image ID. And then finally, that is considered to stop at this point. And one thing, the reason why this is running, ignore the stuff up here. When you do a stop, you're returned, right? Return back to your prompt right here, because you're no longer listening to as a service. Now, you always want to make sure that you're practicing the best practices, which means keeping the minimum on your system possible. If you're following along, go ahead and do Docker images, and then force remove using RMI-F the actual image ID. Now, where is it stored in case you want to move your image elsewhere manually? Well, in Linux, you have varlib, Docker, and Windows is in the program data file under Docker Desktop, and then for Mac, it's under, depending on your virtual machine state is system, you're going to have it under library containers and comdocker.docker. Now, before you move into your labs, I want to give you a brief on what we just talked about and how to link it and why there's AWS Elastic Beanstalk. Elastic Beanstalk allows you to orchestrate all of what your requirements, including really not saying serverless code, but you actually get as close as you want to be. So instead of you orchestrating things using EKS or ECS using Fargate, you'll have all these systems on the back end doing this for you using Elastic Beanstalk. You'll package your code up into an image, such as a Docker container that you can upload to Beanstalk, or utilize the images that are a part of AWS native. My apologies there. My own timer for myself. See if I went over my own time. That's okay. You're a great class. Anyways, the whole point is that you're looking for the ability to load balance. So your infrastructure is right there. It'd be easy to. Your container runtime using a task, which is ECS-based nomenclature. And then you have one more container running. Now, sometimes you might have a front-end task and a back-end task, workers, depending on your actual case, in case you want to do a multi-tier architecture. Elastic Beanstalk allows you to actually self-orchestrate all that based on your specifications from the console, or using an Elastic Beanstalk application, and it will take your container and then do the magic behind the scenes for you. You'll see this in the lab. All right, now it's time to take a break and then go conclude with our demo. Hi, and welcome back from your break. Hope it was good. Let's get to our quick demo. I just want to showcase some of the capabilities of ECS, or Elastic Container Service, from AWS, and solidify some of your concepts that you learned earlier. Now, I'm not going to use the demo because in terms of creating a build or a Docker build image from scratch, you saw that in the slides command by command. So we want to showcase something that's a little bit different and help you complement this information and piece it together in your head. Now, you can go to hub.docker.com, and in this case, I'm looking for the Python runtime. The cool thing is you have tags. Now, the point of Docker files and tagging is that you can actually use versioning. So think tagging to versioning with an alias-friendly name. In this case, you can utilize the latest version. In this case, release candidate 1 3.10, which is not a final, so I'll utilize 3.9.6-buster instead when I do a pull. You can utilize Docker pull, not just Python for the latest, but also the actual tagline instead when you're using Docker pull or run. Now, you'll have to create an account and sign in to actually look at the site with a little more detail. In Windows, you can have Docker Desktop, which will do this for you inside the graphical user interface. Speaking of the Docker client commands, I'm going to show you the ECR, the Elastic Container Registry, where you can upload, push, and pull items as you see fit. Now, here are the commands for Windows and Linux. So I'll use Linux and Windows here because it's just easier. Note that you can actually utilize the login credentials using this information in here. And you can pass the credentials accordingly. Now, to get those Elastic Registry credentialing, you need to go ahead and generate those as part of your repository information. In Windows, you would utilize the PowerShell equivalent. So log in and utilize this. And again, this is your account IT information specific to you. So you can just copy and paste simply to push and pull from the registry. And once you do that, you can actually take that image and then start them. So I'll go to ECS. I've created a sample task right here for you. A task that has, you have EC2 and Fargate and external if you wish. I utilize Fargate because then it's a truly orchestration platform where I don't have to worry about infrastructure or maintaining anything. So I use Fargate to go ahead and do complete control of my task. I want to show you something interesting here, and that's our task definition. Now, remember that just because I have Fargate doesn't mean that I don't have infrastructure at the end of the day. I have my container information here, which includes my commands from what does it look like? Oh, yes, Docker file. It has all that information that I'm looking for. More importantly, if I go to VPC, remember, this is not serverless, so you still have infrastructure. Just because you don't specifically manage it doesn't mean that it doesn't exist. Therefore, my first task is within a VPC right here accordingly. If it's using a VPC, it must have a subnet, and it must have a series of potentially Elastic IPs or NAT gateway or internet gateway for inbound. Here we go, my internet gateway for inbound. So we'll check a look at the load balancer. And then we'll grab my, not the ARN, but the IP address scheme that they gave us. My DNS thing right here. There we go. FQDN. Let's see if it's accessible from the web. And here we go. Our ECS sample application is running. Congratulations. So, utilizing ECS, we can have cloud native cloud orchestrated running of one or more containers, all managed for you. Now, if you're using ECS, the interesting thing about all this is that as you're running your service, a task is a single container by itself. A service is an extraction on top of that. So let's go to our account settings. You can have all this interesting stuff here. If we go back to task definitions, my task definition is essentially how our image is to be ran. If we go to a specific service, here are the services. Notice I have one task, and I can edit that to update that to include additional updates or scale up and scale down. My container port egress is through the load balancing group that's set up for us. Our events here, and we have our auto scaling items that we have to update for, so you have to update the task to do so. Our deployments also include information here, so I'm going to update my service. We'll use the latest provision of my task, which could be a latest tagged version of your image. My service name, and I can include 2 or more for load balancers. Next step, check for healthy period. Well, we'll check it for some item here. So we'll use grace period of 2. So make sure that you've missed certain aspects of it. And configure auto scaling to adjust based on my account. So a minimum should be 1, desired can be 2, and my maximum should be 3. And my auto scaling policy, we target tracking based on my policy auto scaling, my auto policy, and do it based on the average CPU utilization. Our target value should be less than 80%. Save, next, review it, and then finally update your service. Now at this point, it's going to go ahead and update the service and try to add a second task to it. And your task strategies could include bin packing, which includes as many tasks to your EC2 instances as possible. Let's see if we can actually see those EC2 instances, even though it's Fargate. We do have running instance, and it's not managed by us. It's currently in the stopped motion right here, but that's not us. That's actually a different instance. Because you're using EC2 Fargate, and that you don't manage the EC2 instances on the back end, you have no access to this inside the EC2 console. With ECS, you have to utilize the EC2 runtime to actually manage your own EC2 instances here. But that still requires a lot of manual steps, and I'd rather not do that. View the servers. Remember that we'll pay for what we use. We have a running count now of 2 targets on the back end. Let's go back to our load balancer. Our load balancer is right here. Our listener is still at 80. Pointing it over. Look at our target groups. Now we have 2 instances of our container running, all without managing our own EC2 instance. We'll go back to our load balancer, and it's still the same no matter what. So if I overload one, it'll load balance between the 2 accordingly. And this orchestrates everything for me without having me to touch this manually. Now, one thing to note here is if we can get to the strategy, let me look at the task definition or service definition one last time. We have our task running, auto scaling, and interestingly enough, deployments. Now we could actually have a task placement strategy. We can click update. And our placement strategy is usually with him. Switch to a capacity provider strategy rather than have Fargate. And a provider, you can actually change that according to your strategy. I'll use the default cluster strategy, but because we're using Fargate, you can't manually add this to yourself. easily. So let's make sure we cancel all that. Update the cluster again. Not the cluster, sorry. Update the service. Update the service. Instead of trying to add providers and adding external providers if you wish, we go down here to the actual other strategies accordingly right here. We have our service name, we have our clusters, number of tasks, the rollback breaker in case something goes wrong with your updates in here. And let's do a switch to a provider strategy. We'll use a custom strategy, add a capacity provider. Now, because we're using Fargate, we have no provider here, but I wanted to show you the fact that if you're using EC2, you can do a spread, bin pack, one task per host, and other customizations if you're using the EC2 runtime as opposed to Fargate. Okay, I'll cancel out of here, which is the best practice. Now, to go ahead and destroy our cluster because we don't need it anymore, and I don't want to be billed for it. File information in here. Now, we can go ahead and click on the ECS task right here. And then we'll go ahead and delete. Delete the stack. And then go in here and make sure, as you're looking at outputs and resources, that these are being deleted and that you don't have any errors. This may take some time. And although you're not doing this in your lab, I wanted to showcase the different items. Notice that you have public, VPC, subnets. You have all the items that are required for infrastructure to orchestrate it for you. However, as you'll see in future labs, is it always secure? That's it for now. Let's get started on our labs. We'll see you in the next lecture.